As biologists, we all want to work in top-notch research institutions on challenging biological problems, which will have a long-lasting impact on humanity. Truth be told, we all want to be the Newtons and Einstein of biological research. Well, with space biology heating up, space race heating up, and with India landing its rover on the moon, chances are you and your interest in space biology has sparked. And of course, you must be thinking, how can I become a space biologist in the future? In my last video, in fact, that was probably the first video, I said that zoology and botany students will be in hot demand, right? But today, I'm going to talk about a space biological approach, space biology research approach, which is mind-blowing. Okay. Now, this particular approach has come in the manifesto of NASA, which is a space agency in US, as well as ISRO, which is in India, as well as European Space Agency also. So, what exactly is this approach? Now, the name of this approach is fault-tolerant bio-inspired hardware architecture. Now, what does it mean? Now, you all know, like, okay, I was going on the road, I got hurt, right? It's a little bit of blood came, then it got clotted, and now it is healed after a few days, right? The same way, what if, because when we send a rover to Mars or Moon, now we don't have a mechanic over there, right? So who will come and fix things like how we have for the cars? So what if we could have the hardware architecture which could self-heal? Well, right now it seems like impossible. Well, that is where science comes in. Whatever seems impossible is doable, but the right approach, the right funding, and the right people has to be there at one place, right? And that is what NASA is all about. That is what ISRO is all about. And that is what European Space Agency is also all about. So today's video is all about fault-tolerant bio-inspired hardware architecture, where biologists like you can be working. Now let's start this video by looking at the first part. So what exactly you will be doing over there? So you will be working on bio-inspiration. So basically, people who are in marine biology, people who have done research in healing or the human physiology will be in demand, right? Or animal physiology. For example, you have done research on zebrafish or starfish or any marine animal, you will be in demand. So basically, you will be working on interdisciplinary project because you are going to apply the biological systems on physical systems like inanimate thing. For example, this table. So you want to make sure that this table self-heals and comes back if it breaks, right? So research-based concepts, you're going to work with a lot of physicists, you're going to work with chemists and chemistry specialists. And of course, you will be giving the design inspiration to these hardware engineers to develop biological system inspired healing process in these physical instruments. And you will be also providing analogy driven solutions. For example, how a starfish heals within water, how mammal heals on earth, on the land. So all this particular analogy driven solutions you can provide to these chemists and physicists who will implement it in hardware engineering in these spaceships. So that is the first concept, that is the first approach where biologists like you will be working. And for that to happen, you should be a top-notch biologist who has worked on self-healing organisms or any kind of research on humans or on animals where healing is core will be in demand in the future. This is the first approach for self-healing thing. Now, let's go look at the second approach which we have. Now, under this, when you have given the bio-design inspired idea, now the system architecture development has to be there. So basically, you are looking at interconnected system. You're looking at biomimicry. You're looking at devising solutions, a collaborative approach where you're designing the system and ensuring that the proposed self-repair mechanism aligns with the biological principles. The way it happens in biology, the same way it should happen in our this physical world also. So biologists can provide insights into how different organisms achieve fault tolerance and self-repair. And you will be also working on giving some kind of inspiration, some kind of examples on development of bio-inspired self-repair mechanisms in hardware architecture. So now the first was giving the idea, now is the development of that idea you can be working on. That's the second approach under this project. Now let's look at the third approach which we have. Now the third approach which we have is algorithm development, because like our body is connected to brain. The same way the instruments or the rover or the vehicle which is going to go in the space, or the spaceship altogether, or even the satellites, so they all will be connected to a computer, right? So now algorithm development, so that the computer detects that there is a damage and the computer knows how to fix that damage. For example, in science fiction, you would have seen that a spaceship is going and there was an asteroid rain, and then the solar panels got hurt, and now they could heal it, right? The same way. So mimicking biological repair processes, right? So for that algorithm development, so you're going to work closely with computer scientists. You're going to help them adapt the biological principles into the hardware architecture, algorithms that can perform just like living organisms and respond in any kind of damage, whether it is to the solar panel, first to detect, then to repair, and then to cross verify if it repaired in the right way. So that algorithm development, where a computer interface interacts with the physical interface and understands what kind of damage is there and what level of damage is there and whether it can be repaired or not. So this is a huge research field where your understanding of computers, understanding of programming language is going to be very handy. So this is the approach which is going to work. So basically it is like you get in once and you are there in forever in your life in that organization working on these. And it's not just one researcher who can make this happen. There will be a team of like 100 and 200 researchers who will be working on these projects. And just imagine if this is possible, NASA will never face any problem. Suppose a spaceship goes to Jupiter and it breaks down, so it can self-repair and come back, right? So that's a great achievement. So that's where your work will come into picture. Now let's look at the other aspect, and that is material selection. So obviously when you are like if I say, okay, this is leather, right? Or this is some kind of organic material. So somehow we can repair. But what if it is a physical material like carbon fiber? So you cannot really go and heal a carbon fiber. So identifying biomaterials which can withstand space-like or space conditions and still have the regenerative capabilities and should be able to resist the environmental stresses is something where you will come into picture. So material selection and then optimizing this material to survive in that kind of environment. So all of that, so a lot of testing will go in, a lot of fault tolerant mechanisms you'll have to develop, and you'll have to make sure that all this hardware architecture is talking to a computer so that it can detect if there is any damage and then to repair the damage. So that's where, for example, if I'm sitting on this sofa and there is a small, crack, so I can get it repaired by getting it stitched, right? So it's like a skin, right? The same way. So what if that kind of a system is available in the future for the spaceships or the rovers, so that they don't break down, or even if they break down, so how can they repair? So selecting the material for that, so you will be handy there. Now let's look at the next approach which we have, and that is testing and validation. So, okay, you have done the research, you have given the idea, you have developed the material, you have selected the right material, you have developed the algorithm. Now, testing and validation. So, you simulate the environment of Mars, you simulate the environment of, Moon, and then check if under this controlled environment, if it is going wrong or right. Just like how, you must have seen a game is a simulation of the real world, right? So, you're playing a game. So, you put that particular biomaterial based rover in a harsh condition and test it and find out how effective it is. Just to give you example, the Chandrayaan-2 failed, right? What if it had the fault-tolerant self-healing system? It could have repaired itself, and then there was no need of Chandrayaan-3, right? So that's where this will come into picture, testing and validation of whatever you have created. Now, the next thing which is very important, very clear for all of us is, see, you are not going to be a biologist anymore. You're going to be an interdisciplinary scientist. So you're going to work on exchange of perspectives. Like the physicist will say this will work, while the chemist will say this will not work, while you will say that we have to make it work this way. So, it will be exchange of ideas. It will be cross collaboration. It could be something like you are sitting in Europe and the physicist is sitting in US and the chemist is sitting in India or China, and you are collaborating. So cross collaboration across the globe, and of course developing innovative solutions which will further inspire it. It will further advance the research. So interdisciplinary collaboration, inter country collaboration is required to have this kind of technology, and already ISRO is working on it, already NASA is working on it, already the defense departments of various countries are working on it, because when they go at war, right? So suppose their tanks got destroyed, so how could they heal back, right? That's where interdisciplinary collaboration will be required. Now, obviously, while you're developing this, like I said, it can be used in war as well. So ethical considerations also has to be there, because what kind of ecological impact it can have, what kind of biosecurity measures we need to take so that somebody doesn't misuse this kind of a thing, and of course, responsible innovation has to be there. So ethical consideration will also be required, because countries can actually use or misuse this for war purposes. Like they can create weapons which can self-heal. So it can be like the missile goes and hits, then self-heals, and then hits again, right? So yeah, ethical concerns will be there, which needs to be addressed. Moving ahead, while everything happens, everything has to be documented. Everything has to be reported. So documentation and reporting will also be a type of job under this, which will come for you. So yeah, transparency, accessibility, and consistency in all of this is required. Documentation and reporting will be a major and massive task under this project. So let us conclude now. We can say that this is a science of the future. We can say that it requires interdisciplinary collaboration between multiple fields, physics, chemistry, and biology. We can say that if this technology comes into picture, it can really change the face of the world. And we can always say that this will help us achieve expansion and reach out to far planets, right? So with these thoughts, we will end this video. Remember, this video is a part of the Space Biology Exploration series. So next video will be coming very, very soon. Please stay tuned, where we'll discuss other type of jobs which you can get under space biology. And for that to happen, you have to subscribe to Biotechnica's channel. Thank you so much for watching. See you soon in the next one. Till then, keep shining. Bye-bye.